Hey class, in today's lesson we're going to talk about vectors in the plane, which is section 6.3 part 3. Our objective is to write vectors as linear combinations of unit vectors. So unit vectors, so if you see like a vector u, that means that it's going to be a unit vector. And the way we set that up is we say that it's the fraction of v over, or vector v over the magnitude of v. Which is equal to, essentially you can take the vector v at the top and move it to the side and they can become multiplication. So it's 1 over the magnitude of v times vector v. So the vector u has a length of 1 in the same direction as vector v. The vector u is called a unit vector in the direction of v. So to find a unit vector in the direction of vector v, which is negative 2, 5, then we're also going to verify that the result has a length of 1. So the way we would do that is using our formula that v over the magnitude of v is equal to, and these v's should be bolded, it's really hard to do that every time, times 1 over the magnitude of v, that's a v, sorry, is equal to the component vector negative 2, 5 times 1 over, now the magnitude, remember, is the square root of each of the parts of the component form squared. So the square root of essentially negative 2 squared plus 5 squared. And so again, the component form will stay on the outside, so negative 2, 5 stays on the outside. And that'd be 1 over the square root of, well now that's 4 and that's 25, so that's the square root of 29. And I do want you to keep them in square root form unless it's a perfect square. And so as a component form, essentially it's kind of like splitting up this vector. And so this would become then negative 2 over the square root of 29, right? They got distributed. And then comma 5 over the square root of 29. Okay, so this is the unit vector. Okay, and then it asks for us to verify that the result has a length of 1. Now remember, to do that, that's nothing more than using the magnitude formula again. So this would be, if we're going to verify, oh my goodness, looks really bad, the square root of negative 2 over 29, that's square root of 29, squared, plus 5 over the square root of 29 squared. Now the numerators are easy to square. The denominators just become themselves, so that becomes the square root of 4 over 29 plus 5 over 29, 25 over 29. That then becomes, as a fraction, the square root of 29 over 29, and the square root of 29 over 29 is 1. So this actually is a unit vector. Okay, let's keep going. So the unit vectors 1, 0, and 0, 1 are called standard unit vectors and are denoted by I, or bold I, a bold vector I, as 1, 0, and bold J as 0, 1. These vectors can be used to represent any vector v as follows. So if I have a component form of a vector, I could say v sub 1 times 1, 0 plus v sub 2 times 0, 1. And essentially that's the same thing as v sub 1i plus v sub 2j. And so the scalars v sub 1 and v sub 2 are called horizontal and vertical components of v. So the vector sum v sub 1i plus v sub 2j is called a linear combination of the vectors I and j. I think that's supposed to say, I don't know what it's supposed to say. I was supposed to say any vector. Sorry, it's not may. It's any vector in the plane can be expressed as a linear combination of the standard unit vectors I and j. So let's see what that looks like in action. All right, so in example 5, it says writing a linear combination is unit vector. So it says let U be the vector with initial point 2, -5 and terminal point -1, 3. Write as the linear combination of the standard unit vectors I and j. All right, so with this problem, the first thing that we want to do is write our component form of our vector. Right now we just have an initial point and a terminal point. Remember, when we start trying to do the component form, you do the terminal point minus the initial point. So whether you say PQ or if you say XY, our component form for vector U, and this is a bold U, is equal to -1 minus 2 and 3 minus a -5. That's going to give us in component form -3 and 8. Okay, so then to take that unit vector and then to rewrite it as a linear combination, all we do is throw in I and j. So this becomes -3i plus 8j. So rewriting it is not very difficult at all. All right, let's move on to the next problem. And actually, it's our last problem. Example 6 for vector operations. It says let vector U equal -3i plus 8j and vector V equal 2i minus j. Find 2u minus 3v. Okay, this is no different than just plain old substitution. So 2u would be 2 times -3i plus 8j minus 3v would be 3 times 2i minus j. Just be sure that you distribute everything correctly. So if you distribute, that would give you -6i plus 16j. And on the next one, I'm distributing the -3 to both. So that makes this -6i plus 3j. Okay. If we combine i's first and then our j's, that would give us -12i plus 19j. All right. And that is it, guys. If you have any questions, please be sure to come see me for tutoring.